In this lesson, we're going to be reviewing exponent laws that we've learned in previous years and use them to simplify expressions. So just as a reminder, if we have some base to the power of some sort of integer, so let's say a to the power of n, that just means we're going to multiply a by itself n times. So here's a summary of some exponent laws you may or may not have learned before. So the multiplication law states that if we're multiplying two numbers with the same base, all we have to do is add the exponents to simplify it. And similarly, when we're dividing two terms with the same base, all we do with the exponent is just subtract it. Next, we have a power rule. So if we have a to the power of n, all to the power of n, those powers just multiply against each other, and we get a to the power of m times n. The power of a product means that when we have two or more numbers being multiplied together, or variables being multiplied together, and they're all raised to the same power, that's equivalent to each of these factors separately being raised to the power of m. So that means if we were to write a times b out m times, so multiplying them m times, there would be m a's being multiplied together and m b's being multiplied together, so we would just have a to the power of m and b to the power of m. So to make something simple, if we have two terms multiplied together all raised to the same power, we can separate them. So it's almost like distributing this exponent. So we can separate it from one factor to the power of m and times the other factor to the power of m. And similar to when we have a quotient. So two terms being divided all to this raised to the same power, we can break that up into the numerator and all of its factors to the power of m and the denominator to the power of m. And last but not least, we know that when we're dealing with negative exponents, this means that we're just going to rewrite our base as its reciprocal, and raise to the power of m, which is going to be the positive version of our original exponent. So let's try these examples one by one using the rules that we've summarized above. So in our first example, we have the same base, x, all being multiplied together. So we know that we can use the multiplication rule and just add those exponents. So we know that there's an exponent of 1 right here. So our new exponent is going to be 6 plus 4 plus 1, which is going to be x to the power of 11. B is a very similar question. We have two terms, again, being multiplied together. All we have to do is add that exponent according to our multiplication rule. So we have x to the power of 24 plus 9, which is going to be x to the power of 33. In C, we have two terms being multiplied and all raised to the same exponent. So if you look at the power of a product rule, we know that we can this is just going to be x multiplied by itself 5 times and y multiplied by itself 5 times. So we're done here. And our next question is a power to a power. So we know that these two powers, to x to the power of 2 all raised to the power of 3. This is going to be x squared 3 times. This is just going to end up being 2 times 3 times, which is 6. So all we have to do is multiply those exponents together, and we're going to have x to the power of 6. So for the last three examples, E, F, and G, please pause the video and try them on your own, and you can always go up to the exponent law summaries if you need them. Then come back to the video to check your answer. So if you're back with us, you've tried the last three examples, you're checking your answer. Our first example, E, that was just a multiplication rule, so we know we're adding those exponents because the bases are the same, so we're going to have x to the power of 25. Here we have the exact same question, we're just dealing with the negative exponent. But however, you're still going to do the exact same thing. We're just going to add those exponents together, so 10 plus negative 4, that's like 10 minus 4. That's just going to be m to the power of 6. The next one's a little bit tricky, so make sure you've got this one correct. Just like the rule we have above, this product rule, where we have two numbers or two variables being multiplied together, all raised to the same exponent. So this ended up being x to the power of 5, and this ended up being y to the power of 5 multiplied together. Here our terms are m to the power of negative 4, and our second term is n to the power of negative 3. Make sure that you're applying this entire term, the negative 2 to the entire term. So m to the power of negative 4 is raised to the power of negative 2, and n to the power of negative 3 is also raised to the power of negative 2. So notice how we didn't start dealing with these negative exponents in the middle of the problem, we're going to only deal with them at the end because sometimes they just cancel themselves out and then we don't have to worry about it, which is exactly what happened here. So here we have a power of a power, so we know that we are going to multiply those together. And -4 times -2 made 8, and -3 times -2 made 6. And our final solution was m to the power of 8, n to the power of 6. Before we move on, I just want to make sure that we all understand the difference between an exponent written this way and an exponent written this way. So we're going to start with an even exponent first, so exponent of 2. So if I see -3 to the power of 2, this exponent 2 is touching the bracket, which means that what it's saying is everything that's inside this bracket is raised to the exponent of -2. So in this case, this means that we would write everything in the bracket two times. So we have -3 times -3. That's what that would equal, which we know is negative times negative makes a positive, and we know 3 times 3 is 9, so this makes positive 9. This one here, the exponent is just touching the 3. Here it was touching the bracket, so everything in the bracket got multiplied by itself. Here it's only touching the 3, so only the 3 is going to get multiplied 2 times, and this negative is just going to hang on for dear life on the side. It's not included in the exponent party. So we're going to copy the negative, and the 3 gets multiplied 2 times. And so this is going to make -3 times positive 3. That's going to make -9. So these two things are not equivalent, and this is always going to happen when we have a even root. So if we were to write this, let's say that we change this to a 4, and we were to write this 4 times, so 4 negatives would still make a positive. And if we were to have a 4 here, we would have a negative carried below, and 4 3s, which would still make a negative number. So these two statements, or these two expressions, are never going to be equivalent for even numbered powers. Let's take a look now at the next example. I have the exact same integer, -3, but being raised to now an odd exponent. So we're doing to the power of 3 this time. So let's start off with the first guy. We have -3 to the power of 3. That means that everything inside the bracket is going to be multiplied 3 times. So we're going to write -3, -3, -3. A negative times a negative makes a negative, and 3 times 3 times 3 is not 9. It is 27. All right, let's take a look at the next one now. Now the exponent is just touching the 3, meaning that's the only thing that's going to get multiplied 3 times. So we have the negative is just going to be carried down below. So we have negative and then 3 times. And this is going to end up being -27. So the moral of the story is we have to be really careful about what number the exponent is actually really applying itself to. So in this case, it was just applying itself to the 3, and we carried down the negative. Here it applied itself to the -3, and we had to rewrite the negative sign over and over again. So whether or not these terms would be equivalent, that depends on their exponent. So if we have an odd exponent, they will be equivalent, and if we have an even exponent, they will not. Okay, so let's quickly make sure that we can evaluate these expressions. So evaluate means that we're actually going to come up with a numerical answer in the end. So our first example, very, very simple. We have 4 to the power of 3. We just know that that's going to be 4 3 times, and we're going to have 64. Our next one is -3 5 times. So remember that 5 is beside the bracket, which means that everything in that bracket is going to get multiplied by itself 5 times. So we know a negative multiplied by itself 5 times is going to make a negative. And 3 to the power of 5 is 243. Moving on, now we have a fraction to the power of 3. So we can think about this as 2 over 3 3 times. So we could write it out 3 times. Another way to think about it is just to distribute the 3 to the top. So it would be 2 to the power of 3, and 3 to the bottom, so 3 to the power of 3, which would work out to 8 over 27. And finally, for our last example, B, it's really, really tempting to make up our own law that would apply to this, like adding up those exponents. However, if you take a look at the exponent laws that we reviewed, there isn't a law for when we're adding numbers with the same base. So, which means that all we have left to do is just simplify them each individually. So simplify 4 to the power 1 and simplify 4 squared each, and then see what we can do. So we know that 4 to the power 1 is just 4, plus 4 squared, that's just 16. So our final answer is 20. So now let's practice with some variables. So instead of evaluating now, it's asking us to simplify. So we're not going to get a numerical answer, but we're going to get some sort of simplified expression. So taking a look at the first example, we have a product of two different terms, or two different numbers. So we have 5 and then times x squared. It's all raised to the power of 2, so we can just use our product rule. We know that this is equivalent to 5 all to the power of 2 squared. So we've broken up that product and made sure that each of them got squared. So 5 squared, we know what to do with that. We know that that's just 25. And then we have x to the power of 2 all raised to the power of 2. So we know we can multiply those power of a power. We'll be left with x to the power of 4. The next example, B, is very similar to the example that we just tried. So try this one on your own, pause the video, and come back to the video once you think you've got it. Okay, so if you finish your example, you should have this. We've taken all of the products, or every part of this, all the factors, 3, a to the power of 3, and b to the power of 4, and raise them all to the power of 3. So we'll get 27, 3 to the power of 3. A to the power of 9 is a cubed, all cubed, and b to the power of 12 is b to the power of 4, all to the power of 3. If we take a look at the next example, it looks to get slightly more complicated because we're dealing with a rational expression. However, if I were to just deal with the numerator, I know what to do with that, and I know how to deal with the denominator as well. So just work with them separately. And so we know that in the numerator, we have to apply that cube to each of our factors, so 2 to the power of 3, and x squared all to the power of 3. And then in the denominator, we have to apply the square to all the factors, so 2 to the power of 2, and then x all to the power of 2. So in the numerator, we're going to have 2 to the power of 3, which I could simplify, but I notice that I have another 2 underneath that will make it easy to simplify as well. And then I have x to the power of 4 all over 2 to the power of 2 and x squared. So I recognize that I have two different terms that have the same bases. So I have 2 to the power of 3 divided by 2 squared. So I know that I can just subtract those exponents and I'll be left with 2 to the power of 1. And then if I know that these two terms, x to the power of 4 and x squared, have the same base and they're being divided, so I can do the same and I can subtract both of those exponents and I'll be left with x to the power of 2. So my final answer is actually just going to be, and I just have a 1 underneath there, so my final answer is going to be 2x squared. Let's try these next two with a similar strategy. If it gets overwhelming working with these rational expressions, just work with the numerator and the denominator separately. So in the numerator, we've got nothing to distribute, nothing to simplify, so we're going to leave it alone. But there's lots to simplify in the denominator. So it's very tempting. I notice that I have these two terms with the same base. Can I subtract them? And no, because this is not actually a. This is a squared because we haven't applied that exponent. So we can't subtract m in 1. We're going to eventually have to subtract m in 2. So first let's deal with that exponent. So in the numerator there's nothing to do, so we're going to rewrite our a to the power of m times b to the power of 3. All over, we're going to distribute that squared, so we have 3 squared, we have a squared, and we have b to the power of n all squared. So let's keep on simplifying. In the numerator we have a to the power of m, b to the power of 3, all over 3 squared. We've got no other 3's there, so I'm going to evaluate that as 9. And then we have a squared, and then b to the power of n times 2. So this is difficult to say. I didn't really write this clearly. But this is the letter n, and then to the power of 2. So we know what to do when we have a power to a power. We're just going to multiply them. So just because it's a letter, there's no difference. We're just going to multiply n and 2, which is going to make 2n. All right, so next, I notice that I have some terms in the numerator and the denominator that have the exact same base, which means we know what to do with those exponents. We can just subtract the exponents. So for a, I'm going to be left with a m minus 2. So a to the power of m minus 2. And again, in my numerator and denominator, I have two terms with the same base, b. And so I got to subtract those exponents because we're dividing. And we're going to be left with b to the power of 3 minus 2n. And in the denominator, don't forget about this guy right here. We still have a 9 that we can't simplify, so we're going to leave it in the denominator like this. And we are done. So in the end, we have a to the power of m minus 2 times b to the power of 3 minus 2n all over 9. In our next example, the only thing that might look scary is dealing with this negative exponent. However, we're going to do everything the same, and then we're going to deal with that negative exponent at the very, very end. So just taking a look at this numerator, I know I have to distribute this exponent to all of the factors inside of it, and same within the denominator. So we're going to work on that first. So in the numerator, we're going to have 3 to the power of negative 3, and then we're going to have a squared all to the power of negative 3 all over 2 to the power of 2 and a all to the power of 2. So in the numerator, we're going to have 3 to the power of negative 3 times a to the power of, we know what to do with those numbers, we're just going to multiply them. So a to the power of negative 6 all over 2 squared and a squared. So I have two terms with the same base, the numerator and the denominator, so they're being divided. So we know that we can just subtract these two exponents because their bases match. So we're going to be left with equals 3 to the power of negative 3, and then we're going to have a to the power of negative 6 minus 2 is going to be negative 8. And then 2 squared, we know what that is, which is 4. Okay, so there's two things that are a problem. We have this negative exponent here, 3 to the power of negative 3, we're not really sure what that is, and a to the power of negative 8. So we could each write these as reciprocals of themselves. So we could rewrite this as 1 over 3 all to the power of 3. We could rewrite this as 1 over a all to the power of 8. However, a faster way to simplify this would be if we already have a fraction. So this is already a rational expression. We already have a numerator and denominator. When we end up rewriting this as its reciprocal, what ends up happening when you simplify is that this guy ends up being sent down to the bottom of the fraction, and the exponent is now positive, and same with this guy here. So if we ever have a negative exponent in the numerator, all we have to do is bring it to the denominator and its exponent will be positive. Similarly, if we have a negative exponent in the denominator, if we write it as 1 over that thing and we simplify, it's going to end up in the numerator with a positive exponent. So all you really have to do is flip its position, and its exponent will be positive. And again, that's just a shortcut. What we're really doing is we're rewriting this as 1 over 3 to the power of 3 and 1 over a to the power of 8. And we're simplifying, but we're going to get the exact same answer. So I'm going to use the shortcut, which is I know that these two things belong in the denominator, so that's where I'm going to write them. So I'm going to write my fraction bar, and on the denominator I'm going to rewrite 3 to the power of negative 3 as 3 to the power of 3. I have a 4, don't forget about that 4, and I'm also going to bring down the 8, or a to the power of 8, so I have a to the power of positive 8, and the numerator now I'm just left with a 1. So let's rewrite this very quickly. I've got 1 over 3 to the power of 3 all to the power of 4. That's just going to be 27 times 4. And that's just going to be 108. And then we have a to the power of 8, and we're done. So now that we've done this complicated example, these examples here are quite simple. So this asks us to evaluate. So we're going to find a final numerical answer. So we have 5 to the power of negative 2. So we don't have a fraction already, so we can't use our cheat where we just bring it from the top to the bottom, or et cetera, et cetera. So we're just going to rewrite this as its reciprocal. So the reciprocal of 5 is 1 over 5, and we're going to raise this all to the power of 2. So a shortcut that some people do is just rewrite this as 1 over 5 squared. The reason why that works is come back to the proper way, or the real way to do it, which is rewriting this 5 as 1 over 5. But I know that I can rewrite this as 1 squared all over 5 squared. And I know 1 squared is just 1. And so we're left with 1 over 5 squared, which is why this shortcut also works. So we're just rewriting this as 1 over 5 squared is going to work as well. So let's finish this off, and so we're going to be left with 1 over 25. Moving on, we've got 1 over 3 all to the power of negative 4. So we're going to rewrite 1 over 3 as 1 over negative 3 all to the power of positive 4. We know 1 to the power of 4 is just 1, so we're just going to be left with 1 over negative 3 to the power of 4. And we know that a negative multiplied by itself 4 times is going to be positive, and 3 to the power of 4 is just 81. So we're going to be left with positive 1 over 81. Okay, so this guy's really, really simple. We know we have the same base division, so we can just subtract those exponents. So we're left with negative 1. And we know we can rewrite this as 1 over 15 to the power of positive 1, which is just 1 over 15. So let's try evaluating these more difficult guys now. So in our first example here, we have 5 over 6 to the power of negative 2. So we haven't dealt with a fraction before. So what we have to do is we have to write this as its reciprocal. So if I were to write, just as a side note over here, if I were to write 5 over 6 as its reciprocal, it would be 1 over 5 over 6, which is equivalent to 1 divided by 5 over 6, which we know is equivalent to 1 times 6 over 5. So it ends up just being 6 over 5. So just remember, a faster way to write a reciprocal of a fraction is just flip its numerator and denominator. So we're just going to rewrite this as 6 over 5. Let's change this to black here. So we're going to write this as 6 over 5, all to the power of positive 2. And now we know what to do with this. We're just going to make sure that the 6 gets squared, we're going to make sure that the 5 gets squared, and we're going to be left with 36 over 25. So for the next 2 examples, try them on your own and then come back to the video to check your answers. So if you've done it correctly, you should get the same answers as me. Maybe you've done it in a different way, and that's absolutely okay. So for this guy, just remember a fast way to deal with this. You can think of this as negative 1, and you're going to multiply this negative 1 to the power of negative 3. That's also fine. I just tucked up that negative into the numerator of the fraction. And so we flipped and we applied our positive exponent to each of them, and we got negative 9. Taking a look over here, you could flip this and you could apply the positive 2 to the numerator and the denominator, but also a shortcut is if we have 2 numbers with the same base being divided, we know that we can just subtract those exponents. So that's exactly what I did. I just did 7 minus 6, which is 1. And then we'll be left with 2 to the power of negative 2, which we know is just 1 over 2 squared, which is 1 over 4. All right, take a look at the next example. We don't have the same base in these 2 terms, but not only that, we don't have a law that helps us when we're adding 2 terms with the same base. So we know that we just have to work on them separately, so let's do it. So we know how to find 1 over 4 to the power of 0, and we know how to find 1 over 5 to the power of negative 2. Anything to the power of 0 is just going to be 1. The reason for that is, I'll show you an example. If we have 4 squared over 4 squared, we know that that's just equal to 1 because we know it's this something divided by the same thing is 1. We also know it's 16 divided by 16. That has to be 1. If we were to simplify this using exponents, this would be 4 to the power of 2 minus 2, which would be 0. So that means that 4 to the power of 0 is the same thing as 1. So if we find something that's to the power of 0, that means that it was just divided by itself and is equal to 1. And so 1 over 4 to the power of 0, that's just going to be 1. And we know how to deal with 1 over 5 to the power of negative 2. We're going to create the reciprocal of 1 over 5, so that's going to be 5 to the power of positive 2. So we have 1 plus 5 squared, which is 25, and we're going to get 26. In looking at the next example here, it is so tempting to take 2 to the power of negative 1 to the power of negative 2 and 2 to the power of negative 3 to the power of negative 2. But this is not a product. This is being subtracted. So there's nothing that tells us that we have to distribute that in there. So instead, we're just going to again deal with each of these terms separately. Deal with the 2 to the power of negative 1, deal with the 2 to the power of negative 3, and then go from there. So 2 to the power of negative 1, we know that's just 1 over 2, all to the power of 1, minus 2 to the power of negative 3, that's just going to be 1 over 2 to the power of 3, all to the power of negative 2. So we have inside the brackets here 1 over 2 minus 1 over 2 to the power of 3, which is 8. So we can simplify this by I'm going to multiply my denominator and numerator of the first fraction by 4. So we're left with 4 minus 1, which is going to be 3 over 8, all to the power of negative 2. And now we know to simplify this. We're going to make the reciprocal of 3 over 8, which is 8 over 3, and raise it to the power of 2. And we're going to be left with 8 squared over 3 squared, which is going to be 64 over 9.